If you leave a green apple on your desk, you just expect it to be there when you get back.
Right, exactly.
It has this definite independent reality. It's green, it's solid, and it's sitting exactly where you left it, whether you were looking at it or not. But today, we're asking you to completely throw that comforting idea right out the window. Welcome to the deep dive, everyone. We're relying on the incredibly comprehensive Wikipedia article on quantum entanglement to really break down one of the most, genuinely reality-breaking topics in physics.
Yeah, it really is a total paradigm shift.
It is. And our mission today is to give you a shortcut to really understanding this stuff without getting bogged down in all the heavy math.
Right, and I'm here to connect the dots on why this incredibly weird phenomenon is actually redefining how we think about computing and, well, communication on a global scale.
So let's just get right into it. When we talk about particles being entangled, my first thought is like two shoelaces tied in a knot.
Sure.
But this is subatomic, happening across potentially infinite space. So how does that actually work?
Okay, so imagine a single, unstable subatomic particle. Let's just say it has an overall spin of 0.
Okay.
In physics, spin is a fundamental property. It's like charge or mass. Now, this particle decays, right? And it splits into two separate particles that shoot off in opposite directions.
A little explosion.
Exactly like that. And because of this universal rule, the conservation of angular momentum...
The total spin in the universe can't just change out of nowhere.
You got it. The original was 0, so the two new particles must add up to 0 to balance the ledger. That's called the singlet state.
Okay.
So if you measure the first particle on a specific axis and find it to be, quote-unquote, spin up, the other particle, when measured on that exact same axis, absolutely must be spin down.
They balance each other out.
Yes. They are perfectly anti-correlated. You literally cannot mathematically describe the state of one without completely defining the state of the other. They act as a single, inseparable system, even if one is right here in New York and the other is all the way on Mars.
See, okay, I have to stop you there because my deeply logical, classical brain is really fighting this.
Oh, yeah.
Yeah, it sounds, honestly, a bit mundane.
Mundane. How so?
Well, there's that famous anecdote right in the source about the physicist John Bell and his colleague Reinhold Bertelsmann, the guy who supposedly always wore mismatched socks.
Oh, yes, Bertelsmann's socks, a classic.
Right, so if Bertelsmann walks into my office and I see a pink sock on his left foot, I instantly know with 100% certainty that the sock on his right foot is not pink.
Right.
I've gained knowledge about his distant foot instantaneously. So isn't this entire concept just this subatomic version of Bertelsmann's socks? Like the particles were always opposites. We just packed them in two different boxes and didn't know which was which until we opened one.
It is so tempting to think that way. That is actually called the hidden variable theory.
Hidden variables, right?
Yeah, you're assuming that those particles, just like the socks, had a definite state of being up or down all along, just hidden from our view until the moment of observation. But the problem is, quantum mechanics completely destroys that sock analogy.
Why, though? I mean, a particle is a physical thing. Why wouldn't it have a state before I look at it?
Because of the uncertainty principle.
Okay.
A sock is dyed pink at a factory, and it stays pink. But a quantum particle exists in the sort of fluid cloud of probabilities, a superposition, until it interacts with something.
Oh, so it's not actually pink or blue yet.
Right. And the real weirdness hits when we don't just measure straight up and down. Like, what if we measure along different, totally unpredictable axes?
I see.
The properties we are measuring are physically incompatible. You literally cannot measure them simultaneously with arbitrary precision. So it's not an actual correlation of pre-existing traits. It is purely a potential correlation.
Wait, so by opening the box, I'm not just finding out what color the sock is. I'm forcing it to pick a color right then and there.
Exactly. The measurement of one particle doesn't just reveal reality. It forces reality to happen.
Wow.
It causes an irreversible collapse of the wave function for the whole entangled system. When you force your particle in New York to choose a state, you instantaneously force the particle on Mars into the opposite state.
That is deeply unsettling.
It should be.
Well, it makes me feel a lot better about my own confusion because Albert Einstein found this conceptually offensive.
Yeah.
He absolutely hated it, didn't he?
Oh, he despised it. He was fiercely opposed to the implications. This debate was really the crux of a decades-long battle over the soul of physics.
Right.
Back in 1931, he came up with this thought experiment involving a box emitting a photon to try and poke holes in it. And then in 1935, he, Boris Podolsky, and Nathan Rosen published the famous EPR paradox paper.
basically arguing that quantum mechanics must be incomplete.
Yes, they insisted there had to be hidden variables, those pre-existing sock colors that we just couldn't see yet.
And Erwin Schrödinger jumped into the fray right around this time too, right?
Yeah.
He's the one who gave the phenomenon its name.
He did. He wrote a letter to Einstein in 1935 coining the German term for Verschränkung.
Which translates to entanglement.
Right. But what is so vital here is that Schrödinger didn't just call it another feature of quantum mechanics. He called it the characteristic trait, the single concept that forces a complete departure from classical lines of thought.
So what was Einstein so afraid of? If the universe is weird, why couldn't he just accept that it's weird? What did this whole wave function collapsing idea actually threaten?
It threatened causality itself, and specifically Einstein's own theory of relativity.
The speed limit of the universe.
Exactly. Relativity establishes the speed of light as the absolute unbreakable speed limit. No information, no physical influence can travel faster than light. But if you measuring a particle in New York instantly dictates the state of a particle on Mars.
That interaction is happening faster than light. It's happening in zero time.
Which implies a blatant violation of local realism. That's why Einstein famously disparaged the concept as spukhafte Fernwirkung.
Spooky action at a distance.
Yes. He just refused to believe the universe operated by magic.
And honestly, he has a point. So for decades, you have Einstein saying, look, your math is incomplete. The universe isn't a ghost story. And the quantum pioneers are saying, no, the math works. The universe is just weirder than you want it to be. How do you even settle a debate like that?
You wait for someone smart enough to turn a philosophical argument into a testable math problem?
Enter John Bell?
Yes. In 1964, John Bell published what we now call Bell's theorem. And it is arguably one of the most profound discoveries in the history of science.
The moment the rubber meets the road. But how did he actually prove this? Because measuring two particles and seeing their opposites doesn't prove they didn't start as opposites, right?
That's the genius of it. Bell realized you could test the hidden variable theory by measuring the entangled particles along multiple randomly chosen axes.
So not just straight up and down.
Right, maybe tilted at 45 degrees or 120 degrees. And he calculated a strict mathematical limit for how often the measurements would match up if the particles had pre-programmed hidden instructions.
Like a statistical ceiling.
Exactly like a statistical ceiling. It's basically Venn diagram logic. Any universe that obeys Einstein's local realism has to stay under Bell's limit.
Okay.
But quantum mechanics predicted that because the particles don't have set instructions, because they are a single spread out wave function that collapses instantly, they would correlate more often than classical logic allows.
They would break Bell's limit. So all we had to do was run the experiment and see if the limit breaks.
It took years to develop the technology, but Stuart Friedman and Jean Clauser finally did it in 1972 using atomic cascades. And then Elaine Aspect did even more rigorous tests in 1982.
They generated entangled pairs and measured them along rapidly switching axes, and nature disobeyed the Venn diagram.
It shattered it. They statistically violated Bell's inequality. They proved that local hidden variables cannot explain the correlations.
So Einstein's version of a strictly local, predictable universe was definitively dead.
It was. Elaine Aspect, John Clauser, and Anton Zeilinger actually won the 2022 Nobel Prize for this work.
Okay, so my sci-fi brain instantly jumps to the implications here. If I have a particle in New York, and you have one in Tokyo, and they're instantly correlated across space, why am I paying for a cell phone plan?
A quantum telegraph.
Yeah. Why can't I build a faster-than-light phone? I put my particle in a machine, I force it to spin up, which instantly forces yours to spin down. We assign binary ones and zeros to the spins, and boom, we have instantaneous Morse code across the galaxy.
It is the ultimate dream, but unfortunately the universe has a built-in firewall against it. It's called the no communication theorem.
But the connection is instant. If my flip causes your flip, that is communication.
The catch is the word force. You cannot force your particle to spin up. The outcome of your measurement is entirely fundamentally random. You are essentially rolling a quantum die.
Oh, so I measure it, hoping for a 1 so I can send you a message, but it might just be a 0.
Right. You roll the die, and let's say it lands on 1. Because of entanglement, you now instantly know that my die in Tokyo is showing a 0.
Okay.
But because you couldn't control your outcome, you can't encode a message. To me, sitting in Tokyo, my die just looks completely random. I have no way of knowing if my particle is in a state of 0 because you measured yours, or if it just happened to collapse that way naturally.
So I wouldn't know if it's a message or just static.
Exactly. The only way we can verify the entanglement is if you call me on a normal, slower-than-light telephone and tell me what you rolled.
So Einstein lost local realism, but relativity holds. The speed of light speed limit is preserved for actual information. We can share a spooky connection, but we can't use it to gossip faster than light.
Right, causality is preserved.
That feels like a massive compromise by the universe. If we can't use it for a galactic telephone, what is the practical value of all these entangled particles?
In modern quantum information theory, entanglement is treated as a highly valuable, expendable resource, like a specialized fuel. It enables something called LOCC, which stands for Local Operations and Classical Communication.
And what does that let us do?
The most famous application is quantum teleportation.
Teleportation. Now, we have to clarify this before anyone gets too excited. Are we talking Star Trek beam me up, transferring physical matter, or is this something else?
It's a bit different.
Let me pitch an analogy. Is it like me calling you on the phone to tell you how to build a Lego set exactly like mine, but the quantum rules demand that my original Lego set violently explodes the second I read you the instructions?
That analogy is surprisingly accurate, especially the explosion part.
Really?
Yeah. In quantum teleportation, you aren't moving physical matter. You are transferring a quantum state, the exact fragile properties of a particle.
So how does the entanglement act as the fuel for this?
Let's say Alice wants to teleport a specific quantum state to Bob. They already share a pair of entangled particles. Alice takes the particle she wants to teleport, and she performs a joint measurement on it together with her half of the entangled pair.
And that measurement is the explosion.
Yes. Because measuring a quantum system collapses it, the act of reading the information permanently destroys the original state in Alice's lab.
Wow.
This is a fundamental rule called the no-cloning theorem. You cannot perfectly copy an unknown quantum state. It must be destroyed in one place to exist in another.
So Alice measures them, destroying the original, and then what?
That measurement produces a set of classical data, just regular ones and zeros. Alice sends that data to Bob over a normal light-speed connection, like fiber optics.
Okay.
Bob receives the data, applies a specific mathematical operation to his half of the entangled pair, and his particle instantly transforms into an absolutely perfect, indistinguishable replica of Alice's original particle.
I am sacrificing my Lego set to the void, just so you can reconstruct it on the other side. That is beautifully tragic.
It is.
But wait, if we can teleport states using entanglement as a bridge, can we manipulate things we've never even interacted with?
We can. This brings us to a mind-bending process called entanglement swapping. You are essentially teleporting entanglement itself.
How does that work?
Imagine two completely separate pairs of entangled particles. Pair 1 is particles A and B. Pair 2 is particles C and D. These two pairs have never interacted. They were created in different machines.
Okay, two isolated couples.
Now bring particles B and C together and perform that same joint measurement we just talked about. By measuring B and C together, they become entangled.
Okay, but what about A and D?
That's the crazy part. The remaining outlying particles, A and D, suddenly collapse into an entangled state with each other.
Wait, A and D are perfectly entangled, acting as a single quantum system, even though they have never, ever touched. You're literally matchmaking particles across the void.
Yes. You've created an entangled link between 2 points in space that have no direct causal history. And if you think that's wild, researchers have used this underlying logic to do things that sound like literal magic, like the 2014 ghost imaging experiment led by Gabriela Barreto-Lemos.
Ghost imaging? That sounds like snapping a Polaroid of a poltergeist.
It's not far off. They managed to produce a visible image of an object using light that had never physically interacted with that object.
How is that physically possible?
Oh.
A camera works because light bounces off an object and hits a lens. If the light never touches the object, where is the image coming from?
You use two pairs of entangled photons. Let's call them the red photons and the blue photons. You take the red photons and fire them at your subject. Let's say it's a stencil of a cat.
Yeah.
Some red photons hit the stencil and are blocked. Others pass through the cutout.
Okay, so the red photons now hold the shape of the cat. So we just point a camera at the red photon.
No, we throw the red photons away. We don't measure them at all.
What do we look at?
We look entirely at their entangled partners, the blue photons, which have been kept completely isolated in a different part of the lab.
Right.
Because the entangled pairs are perfectly correlated, when a red photon passes through the stencil, its blue partner registers on a highly sensitive coincidence detector. By mapping out only the blue photons whose partners successfully pass through the cutout, an image of the cat emerges.
You're extracting a photograph of a cat from photons that have never been in the same room as the cat.
Exactly. The information is transferred entirely through the non-local correlation of the entanglement.
Okay, my biggest hang-up here is that this all sounds incredibly fragile. For decades, the defense against quantum weirdness was that it only happens in a multi-million-dollar vacuum chamber. The moment a subatomic particle bumps into a stray molecule of air, the magic breaks.
Right.
If entanglement is so fundamental to the universe, why don't I see ghost images and teleportation when I walk down the street?
You hit the nail on the head regarding fragility. The reason we don't experience this in the macro world is due to a process called decoherence. When entangled particles interact with their environment, bumping into air, interacting with heat radiation, or even just being measured by a clunky classical instrument, they become entangled with that massive, noisy environment.
The signal gets lost in the static.
Exactly. The specific fragile link between the original particles diffuses into the background noise of the universe. However, our technology is advancing so rapidly that the neat little wall we built between the weird quantum lab and the normal classical world is completely crumbling.
Really?
Oh, yeah. We are scaling this phenomenon up across unbelievable extremes.
Let's talk about that scale. Because we're not just doing this on tabletops anymore, are we?
Far from it. In 2017, the MOSHUS satellite distributed entangled photons from orbit to ground stations in China.
Wow.
Yeah, maintaining the quantum link over a record 12,203 kilometers. We are successfully beaming this delicate connection through the atmosphere from space.
So distant is clearly no longer a barrier. What about the types of particles? Are we stuck with just photons of light?
Not at all. We're seeing it in the most extreme physical environments imaginable. In 2023, the ATLS detector at the Large Hadron Collider successfully measured entanglement in top quarks.
Top quarks. Those are insanely heavy and exist for a fraction of a second before decaying.
Exactly. Measuring entanglement at those extreme energy scales proves that this isn't just a low-energy quark. It operates at the absolute frontier of high-energy particle physics. Furthermore, physicists at Brookhaven National Laboratory have demonstrated that the quarks and gluons inside protons are entangled with each other.
Meaning the very protons that make up the atoms in my body aren't just bags of loose parts. Their internal structure is fundamentally held together by this interdependent web.
Yes. And perhaps most astonishingly, we are scaling up in actual physical size. Well, in 2011, researchers successfully entangled 2 macroscopic millimeter-sized diamonds at room temperature. And in 2020, they reported quantum entanglement between the motion of millimeter-sized mechanical drumheads.
A millimeter is massive. You can see that with the naked eye. You don't need a microscope to see a millimeter.
It proves that the laws of quantum mechanics don't suddenly turn off when things get bigger. It just gets exponentially harder to shield larger objects from the decoherence of the environment. But as our engineering improves, the boundary between the quantum world and the classical world is being revealed as an illusion.
We have gone from Albert Einstein furiously writing papers to disprove spooky action at a distance, to a reality where we are literally engineering it. We are teleporting quantum states by destroying the originals. We are snapping ghost images from shadows. We are linking vibrating drumheads and satellites in orbit. It makes you wonder, if everything was packed into an infinitesimally small point during the Big Bang, isn't it possible that everything is entangled?
That intuition points to one of the most mind-expanding concepts in modern physics. If you want to know how deep the rabbit hole really goes, we have to look at quantum field theory, specifically the Riesch-Schleider theorem.
I am strapped in. What does the theorem say?
In quantum field theory, we don't really view particles as isolated little billiard balls. We view them as temporary excitations, little ripples in underlying fields that stretch across the entire universe.
Okay.
The Riesch-Schleider theorem suggests that entanglement isn't just a rare phenomenon we carefully manufacture in a lab or inside a particle collider. It mathematically implies that the vacuum state itself is highly entangled.
The vacuum state. You mean empty space?
Yes. The state of absolute lowest energy, what you and I would call complete nothingness, isn't empty. It is a bubbling soup of quantum fields. And the theorem suggests that any local region of this vacuum is profoundly entangled with any other region, no matter how far away.
Wait, so if I just look at the empty air hovering above my desk, you're saying that nothingness is actually an infinite, invisible web of entanglement tying the fabric of the universe together?
The math strongly points to that conclusion. Local operations on the vacuum in one region of space could, theoretically, be correlated with any other region. The very emptiness of space is structurally defined by these non-local quantum connections. The universe isn't a collection of separate things. It is a single, inseparably woven tapestry.
I think my brain just wave function collapsed.
Yeah.
I started this deep dive talking about the comforting local reality of a green apple sitting on a desk. But knowing what we know now, that beneath that solid green surface, inside the protons of its atoms, and even the seemingly empty air surrounding it, there's a spooky, instantaneous dance happening that links it to the rest of the cosmos. I don't think I'll ever look at an apple the same way again. The illusion of isolation is completely gone. So, something for you to mull over as you look at the empty space in your room today. Keep diving deep, everyone.